Now, some properties that big O notation has that helps us find big O of more complicated functions. So we've done big O's or sort of polynomials using that definition. And what happens if there's more complicated functions? So some properties that they have are that if little f is big O of big F and little g is big O of big G, then what do I do about the sum? Well, it is big O of the max of big F and big G. So basically, when you're adding two functions together, you take the larger one. You take the larger big O, whichever it is. And you can think about the larger in terms of which functions grow the fastest at the end. We're going to show a graph of comparing functions, but think about them like higher powers grow faster, exponentials are even faster than that. Kind of think about which ones grow the largest by which is fastest at the end. So when you're talking about big O and you're talking about worst case and you're adding two things up, you want to take the maximum of those two things and ignore everything else. When you're doing a product, then you're going to multiply. So you just multiply big O of each. So this will be big O of F times G. So how can we use that? So here's a function. It's n log n plus 2n times n squared plus 3. And if I want to find big O of this function, I'm going to find big O of each piece first. N log n is a little bit bigger than 2n, so n log n is going to be this first one. And then n squared is definitely bigger than that 3. And those were sums, right? So I took the largest of each of those sums. And now when I do a product, I multiply them together. So this is going to be n times n squared makes n cubed log n. So a good big O estimate for this function is n cubed log n.